Hey, hey!
Today he's going to talk to us about demystifying memory management and profiling in Node.js. Looking forward to it. Thank you, Ruben. You're off. Awesome.
Hello, everyone. I'm Ruben. Thank you very much, Benji, for the introduction. As you said, I'm a Node.js TSC member. I work as a principal software architect at myBonWolf. And without further ado, you also already know the topic. It's demystifying memory leaks. So who has actually not run into any memory leaks? Most of us have probably seen them at least once during our work time. But are they actually scary? And should we fear them? So before I really can answer that, I have to know what a memory leak is. And to answer that, I will just check Wikipedia, and it says a memory leak is when a computer program incorrectly manages memory in a way that memory which is no longer needed is not released. So we will build up memory, and then our process at some point has no further memory to allocate, and it might crash. This is the worst case scenario. And this is how it would look like if you just put it on scale. So over time, on the blue line, we clearly have a memory leak because the memory usage increases. Opposed to that, there is the yellow line, which is pretty much a flat line. And that is how ideally most programs should run. Sometimes they might have some spikes and go up and down, but as long as you can put pretty much one line that is relatively flat, everything is good. If it goes up, and then you clearly have a memory leak. So is it possible to prevent memory leaks in general? I would like to take another quote to answer that one. And in this case, of course. Well, the cheapest and fastest, most reliable components are those that aren't there. So if we don't code, if we don't want to have any computers, then we won't have a memory leak. Otherwise, it's going to be very difficult to not run into them from time to time, but this is not that bad. And before we still are able to answer how to deal with these memory leaks, maybe we should know how memory in JavaScript is dealt with in general, because we don't have to think about it in our average day-to-day work, right? We have a variable, we assign something to it, some data type, some value, and then the computer is just allocating the necessary amount of memory for that data type. Sometimes it's a bigger value, sometimes it's smaller, depending on what you want to do. And implicitly, we have a garbage collector that checks if our allocated memory is still referenced somewhere from our root object. Because everything in JavaScript is in the end connected to the root object. When you're in a browser environment, you know it's the window object. And when you're in the Node.js environment, it's the global object. Or in modern JavaScript, you could also say global this. And somehow, everything is connected to that. Now we can check if the memory is connected, if the data is still somewhere in that tree that we built or not, and otherwise we free it. Though some ways of handling our garbage is more efficient than others, and also sometimes we might miss some cases. This is obviously not ideal. So V8, which is probably the most sophisticated one out there, it's built by Google and it's used in Chrome and Node. And we have the garbage collector inside of V8 because it's a just-in-time compiler. And it has something that is called heap memory. And the heap memory is split into 3 different parts. We have a young generation, which is only a small part of memory. And every new variable that we assign a value to is immediately put into that young generation. And there is no garbage collection yet, right? Because we just allocated it. And then we have very frequently going an algorithm through to check if those allocations are still required. Because most of the time in JavaScript, we want to dispose all our allocations right away again, because they are only like an intermediate step to get to where we really want to go to. And only a few objects have to stay there a long time. So when the object has not survived a first garbage collection run, a scavenge in this case, then it will go into the intermediate generation. And if it survives a second time, then it is moved into the bigger heap part, the old generation, also called old space. And we have a different algorithm to go through that memory, which is more computation. You have to invest more CPU time to check all these, also because it's a lot bigger. And we believe that this memory is likely rarely freed. Most of the time, we have to still use that. And to give you an overview of how this works, in effect, it's called, this is the Mark Sweep algorithm. We have the garbage collector root object, and then we just use maybe a recursive algorithm where we check each node that is somewhat connected to the root, if it is connected, and all other can be thrown out. If you are interested in more of the memory management, I can recommend to open the webpage that I linked here. It's a very nice article. Check it out. So, okay, we know how memory handling works somewhat. It's done implicitly. It's we don't have to worry about it. There are these minor GCs, the fast ones, which are called scavengers, and there are major garbage collection runs, which are called Mark Sweep. And this is great. Now we know that we don't have to worry about it because it's always done for us, right? But we still have those. And which memory leaks or issues exist? I put together a list here. In this case, it's not an exhaustive list, but it's one where I believe most frequently people run into. First of all, it's the closures. In JavaScript, we have a lot of closures, and sometimes it's tricky to identify how objects are interacting with each other and when they are really still referencing each other. And we can confuse the garbage collector in a way that it is not aware that memory should not be used anymore. And we have file descriptors in the Node environment which are not closed. So if you open up a file descriptor with the file system calls, and then you could maybe write something into that file descriptor or read something from it. But if you don't close them, you will not be able to open up files at some point anymore, because a system has limited file descriptors available. On a Unix system, the default is normally 1024 entries, and if you exhaust them, well, that's a bad thing. Then the third type is just wrong data types. Let's think about the caching, a cache that has no boundaries, that may increase infinitely. In that case, we just write into it and write into it and write into it. And because there's always a hard reference to all of the different objects to the root object, then we are not able to free that memory, and we might end up in a crash. And there are also sometimes just bad algorithms that might allocate more memory in general, and we have to pay attention to that. So the fourth one is eventlessness. We have them both in the browser, and we have them on Node.js side. On the browser, you have something like document attach event listener. I forgot the exact command. And in Node, it's normally you have the events, and you say .on some name, and you have a new event listener. There are also some very tricky parts where you have to know the concrete V8 implementation details. And I'm going to show you a nice example where people are probably not aware of this implementation detail. And sometimes we just fire so many things in parallel especially with JavaScript, that is a language where you want to do things in parallel, that we sometimes build up too much memory at the same time. And that is also an issue. To go and show you some concrete examples, here we have the closure, for example. We have two variables, let and foo, count and foo. We assign 0 to count, and we have a function run. And when we execute run, we have internal variables that are only local to the run function. But here we assign to the inner variable, original, the outer variable foo. And then we have another one, and that is called increase as variable. It's actually a function. And here we reference only the internal variable original. So in this case, we only check internal variables in total in this function. But we confuse the garbage collector altogether with how it is built up, that it is not able to identify those as being releasable anymore. And foo is going to be there all the time. Each execution is going to allocate a new huge array that is a big string in the end, because we allocate a lot of entries that we join with foobar as string. So we are going to build up memory fast here. With the file descriptors, we are able to open one file, and we are writing something in there, but we are not going to close it. This is done implicitly on garbage collection in Node.js, and we are going to print a warning by default if you don't close the file descriptor, because we want every user to do it explicitly. But you're able to circumvent warnings, and this is always a bad case. So please always pay close attention to the terminal, also on your production system, if anything like that shows up. Why is it bad, though, that it is only happening on garbage collection? Garbage collection is something very unreliable. You're not able to know when your memory is freed. You might think, okay, the implicit behavior is totally fine, you know, but sometimes the garbage collector might just not trigger a mark sweep, and the memory is already in the old space. And then your application is going to allocate a lot of memory. And we don't want that. It's expensive. It's slowing down your application. It might get very costly if you think about cloud environments and things like that. Here it would look like how it is fixed, because we are having a finally block. And in that finally block, we are going to close the file descriptor, which is how we should do it right away. That way, there is no question for the garbage collector, because as soon as it's collected, well, it realized the file descriptor was already closed, all good. And when we read very big data in memory, for example, when you have an HTTP server, this can also be an issue. I've seen this code really frequent. It's something very, very simple. Imagine you have a file that is like 5 MB big. It's not that big, right? You can read it in memory, but now imagine that you have lots of concurrent users at the same time. If you read the whole file all the time in memory, and it's not only going to be 5 MB, but it's going to be 5 MB to the number of concurrent users that you are reading this file in, and then we are sending it out, and we are not going to free any of that memory until we completed our response, and that might take some time as well. So we should instead just use streams, which will create a nice flat line, because you're also going to improve the performance of your application by you read something from the database, and you're immediately going to send it out to the user, just that small chunk that you read. And now there is nothing going up and down. You can have a lot of concurrent users, because it's only going to have a very small memory overhead. With event listeners, obviously something, all these examples are a bit made up, but and we have just one database that is event-driven, why ever. And we have an HTTP server again, and we on each request, we want to know when data is received from the database, because we also write something to the database, and at some point it's going to respond. But as soon as you call that, it will add one to the database in general, and not only locally. So it's not for the single HTTP call, but you will have lots and lots of data event listeners. And even though they might not be big in memory, they will build up over time. And this is the example that I told you about V8 implementation details. So when you have a string and you have a simple string, you allocate, let's say, test. You want to have test, that's it. And you assign it to the variable foo. Good. That's not a lot of memory. And now we want to concat that variable with another string that is again test. So what we could do is we could allocate a complete new chunk of memory that is the size of both strings together, then write both strings into the new memory chunk, and then expose the old ones. And as you see, this is a very expensive operation. And instead, what is done is, and there is an internal V8 data type, and that is called a const string. And in this case, we just reference both strings and say we have a tree beneath us, and one type is test and the other one is also test. And now we are able to have test because we concatenated them. It's behaving similar when you slice something out. So we don't expose the rest of the string. And in this case, we only slice out a very small chunk of the string that was generated, and the rest is still going to build up on your memory. And this is one of the most frequently complained things about on the V8 issue tracker, but it is, in most cases, a very good way of dealing with it. Why? Because it's a heuristic. You have to decide if you want to be 100% correct or if you want to gain that extra performance. In most cases, the extra performance is more important, and that's why it is implemented that way. Not knowing about this thing might end up in some very hard to debug issues, though. And we know we should not litter our environment. Still, we do it day after day, and we litter our programs as well with garbage. But when we do that, sometimes our applications are going to crash because the memory limit and the amount of garbage that the environment is able to handle is just too big. It's too small, in this case. And this is going to be frustrating. But it's not only about your own code, it's also we have a lot of different modules. Sometimes we build modules for other people, and therefore paying attention that you don't have a memory leak in your code is really important. Also when you're also of a small library that other people might want to use. Because when you debug your code and you have to collect all their memory, as I said, it's a frustrating job, and sometimes you spend hours and hours to just trying to figure out what code part your memory was not freed upon. And yeah, I cannot recommend that. You might get anger issues, just similar to some people who have to deal with garbage. Now let's get to the most important and interesting part. How shall we actually detect and fix those memory leaks? Well, we have a couple of tools and flags in Node.js that will help you to identify those. The most important part is the inspect flag. You can then connect, for example, the DevTools with your Node environment, and you are able to inspect the memory of your process live, and you are also able to collect, to inspect, for example, so-called heap snapshots. A heap snapshot is at some point of time a concrete snapshot of all allocated memory in your application. And now you're able to look through what is in there. And with the inspector and the DevTools, you're able to compare those to see what was added from your first heap snapshot to the second. But be aware that this is a very costly operation to go through all the memory on your heap and to build the snapshot in this case when you have a lot of memory. So it's not good to use those in production in most cases. If you have to be very, very reliable and you want to identify some difficult to debug problems, you might want to use the abort on uncaught exception flag. It is going to cause a heap dump generation in case your process is going to crash. And then you are able to do some so-called post-mortem debugging, where you identify the issue later on due to being able to see what was the current state of your application and to see what objects were alive, what strings were there, and so on and so forth. Node is another tool that allows you to inspect such data, and there are a lot more. They all pretty much do a similar thing. Some you might even look at them in Visual Studio Code. You can find a lot of these tools on the Node.js.org website. I recommend you to go there and to check some out. But just be aware, there is not really a lot of advantage normally from one tool to the other. It's more like which one you prefer on your own, but they all do a similar job. Let's get to some small coding example. I want to show you some of the parts that I told you about. Let's start with, for example, the string crashing one. So strings crash. Let's have a look at that. The code is very simple, as I showed you early on. Right? We have an array, and we just gather up the small slices that are only 20 characters long. And we do that in 10,000 times. And it should not be a lot of memory. Let's check it out when we have Node running. It's a new Node version. It collapsed. Allocation failed, JavaScript heap out of memory. And we can also now use a flag, trace GC, to see what was going on during the time. And this is pretty helpful. So here we see the scavenge calls, the ones that I've told you about that are very fast, going to be triggered frequently. And we see they are really frequent compared to a mark sweep, which is here. And then we have a lot of scavengers again, and so on and so forth. What is happening at the end is that the garbage collector has a lot more frequent mark sweep operations, because there's almost no more space on the heap left, and the heap is something fixed size. So at the moment, the maximum number of memory on the heap is normally 2 gigabytes. And there, it's a magic value from the V8 team. And it is normally completely sufficient to have that limit. If you run out of your memory in that case, there's definitely something fishy going on. It should not require such an amount of memory. So now we know we can see how efficient these mark sweeps, etc., are going on. Let's also have a look at some other examples. Check read file. I have other ones that are nice. Which ones? Memory leak closure. Right. So here, it's the earlier example as well. Count and foo and run. And let's check this out. So what is happening in this case? We have one execution of run per millisecond, and each 2 seconds we write a heap snapshot. And now I want to inspect these heap snapshots. So I'm going to run node with --inspect, and now the debugger is listening on a WebSocket, and I'm going to go here, Chrome inspect, and then it says here open dedicated dev tools for Node. So I'm going to click on that, Nice. Now I have the DevTools open, and it says here I have the memory profiles, and I'm able to select different types of things. I can take a heap snapshot from here. I can allocate, do allocation sampling, and so on. But I want to load a profile because I'm generating heap snapshots every 2 seconds. So I'm using the first one, and I want to compare it with the later one. And I'm going to stop the process. As you can see, the size of the first heap snapshot was 2.2 megabytes, and the last one is actually 5.9 megabytes. So this contains a lot of things that are not so easy to read at times. And you have a list where you can obviously sort by percentages and size and so on. And it has some content. We know, okay, func is often here. But do we actually know that this is the bad part? No. So we don't want a summary in most cases, but we want to go to the comparison part. Let's click on that. And now we are comparing it to the base snapshot, which is the first one. And here we see we have a lot of concatenated strings with a huge size. It's actually 3 megabytes that is allocated. And that makes sense because we had 2 plus 3 is already 5. And when we look at them, it's not only 20 characters. It's the complete string that is contained here. So we have our leak. Now we want to identify where this is actually coming from. And we can check this down here easier. Because we see, okay, it's called in func. Oops, let's go to the complete entry. Yeah. So in this case, it's in the array. And this is has some other parts that are from V8. And here we see it's called in a function func. And we know the function exists in there. And there it's allocated over and over again. And we are able to identify it relatively easy this way. So please use that. It's probably the easiest and most straightforward way to identify memory leaks and to fix them. Because you are able to look at the actual value of the memory. Please also be aware, when you take heap snapshots, all memory is going to be in there, no matter if it's something that is that should not be exposed to anyone. Like if you have some secrets in there, be aware this is going to be contained in there. So don't provide any access to this information outside of your system. Right, so let's go back. So now we know how to fix memory leaks, because this is pretty much all there is to it. Yes, there are some tools which make it a little bit easier, but mostly just used in the DevTools, and you will be very happy. You can do this not only for Node, you can also do this in a browser, and it will work just as fine. Then there's one more part that I did not yet speak about. It's called an APM, Application Performance Monitoring Tool. I highly recommend any production system that it should be high available and that is frequently used to have such a tool that monitors your process for memory usage, CPU usage, and likely also error frequency, what errors happen, and so on and so forth. And you can then be notified easily about issues when, for example, your memory goes above a specific threshold. Yeah, and if that happens, just profile your application, take some heap snapshots, compare them, identify the leak, and fix it. Those are the steps. What else is there to it? We know we have a lot of different tools to identify the leaks. We know memory is expensive. Be careful about it, especially in cloud environments. It could be very expensive. And heap snapshots are normally not there to be produced in production. I'm going to show you one more part right here, because the code that I executed also contained a way to generate the heap snapshots during runtime from your application itself. So in this case, I'm loading V8, and it's a module from Node.js, and I'm going to use the write heap snapshot function from that module. And that will just write down that snapshot to disk in a specific format. As you can see, it's in this specific naming way. You can read about it in Node.js documentation. And there is also another function that could be used to just get a stream for that snapshot, which is a little bit less expensive in a way because you don't have to write it down into file immediately. But it's still a blocking process. You will have some latency in your application, and don't call this function too frequently. But sometimes it's very, very hard to reproduce a memory leak without being in your production environment. And therefore, in some cases, generating these heap snapshots might be a way out to identify it quicker. What else? Yeah, please be careful to choose the right data type and the right data structure. And yes, some people say restarting your application on memory leak is fine, but please just use something like the DevTools and the inspector to identify the leak and fix the issue instead of just keeping it around. And sometimes people are afraid of memory leaks because they do not know about these tools that they exist. It's not really that difficult in the end. So thank you very much for being here. I hope you enjoyed the talk. I want to end my talk with another quote from a computer science pioneer, Ken Thompson. And one of my most productive days was throwing away 1,000 lines of code. I can very well relate with that. It's always a great feeling to reduce code. So yeah, stay safe.